All right, so with our worksheet packet, yesterday we looked at a numerical way of calculating information from a table. Now we're going to look at a graphical method. So this graph represents the velocity in feet per second of the particle moves over the x-axis in the time interval from 0 to 9 seconds. Because the graph starts at 0, because that's got the point 0,3 here, and it ends over here over 9 down -6, I believe is how much that is. I think it's going by ones on the y-axis. So this is a velocity graph. This is when the velocity is positive, when the velocity is negative. We know when it crosses the axis, that tells us something. We know when it has a max or min, that tells us something else. We also know that if it's increasing or decreasing, that tells us something as well. You might have to go back and look at the worksheet we did on the first day sometimes if you forget what's the relation between position and velocity, or velocity and acceleration due to the positive, negative, or increasing, decreasing relationships. We did a lot of information on that first page that told a lot of that, so if you can't remember something, look back at that first page and see what's the relationship, and then see what it's doing on your graph here. As you go through, I wanted you to think about 2 or 3 things. One, is it something I can just look up one point on the graph and see what it's doing? 2, is it something I can look at over an interval to see if it's increasing or decreasing? Is it got a positive value for the velocity, a negative value for the velocity? Or can I use that trick we used yesterday with the table? Can I pick a couple of points and find the slope of something that's not really obvious off of here? Those are the similar things that you did yesterday with the table. You should be able to do similar things with a graph. And as you look at the graph, you have to keep in mind that this is a derivative of the position. Okay? So that derivative of the position formula gives you that velocity graph, which is what this is. And of course, the maxes, mins, inflection points, the x-intercepts, the increasing, decreasing tells you something about the next derivative. So I want you to read each question and see how many of those that you can answer because you know how to look it up on the graph, or you can do a small calculation. Based on what we've done on the previous 2 lessons, you should be able to answer some of these. So I'm going to give you a little bit of time to read them and answer those questions, and then we'll come back and we'll discuss. All right, let's see where we're at so far. So from a graphic point of view, it says at t equals 4 seconds, is the particle moving left or right? So what do you notice about 4 seconds when you look at the graph itself? Okay, the slope is decreasing there. What's the value at 4? Okay, those are 2 different thoughts, and they tell you totally 2 different things. The value tells you one thing, and the decreasing thought tells you something else, okay? And in this question, velocity is all about speed and direction. So when you said 6, that means you're going 6 feet per second, and when it's positive 6, you're going to the right. If you're talking about the descent of it, you're talking about acceleration. When the lines go up and down, increase or decrease on a velocity graph, that tells you something about acceleration. So this question wanted to know, is the particle moving left or right? And that's just the value of the problem, because this is a velocity graph, and velocity tells you direction. So all you had to say was at t equals 4 seconds, the particle's moving to the right because the velocity is positive. Now, in the second question, it says over the what time interval is the particle moving to the left? Well, we know the velocity is negative, makes the particle move to the left. So all we have to do is see What two numbers is that happening on? Exactly. Now, how do you write that?
I put the closed bracket.
Okay, so you gave it an interval notation.
I put 5 less than or equal to 2.
Did you write it between?
Yeah.
5 is less than or equal to 2 is less than or equal to 9. All right, be careful. I don't think you can say it's equal to 5. I think you're okay on the 9 because 5 is 0. And you don't want it to be 0, you want it to be negative. So you wouldn't need an equal mark on the 5. But you would on the 9 because it's negative. So you could do a between, or I think you could do interval notation because it says over the interval, and those are two proper ways to tell an interval. But you wouldn't have a bracket on 5. You'd have a parentheses, a bracket on the 9. All right, the third question said, at t equals 4 seconds, is the acceleration of the particle positive or negative? Explain your answer. So this goes back to what we were just discussing when we were discussing number 1. Acceleration on this graph is all about increasing or decreasing. Because when your graph is increasing, based on what we studied back on the first day, I believe. Hold on, let me read that sentence to you. If the acceleration of the particle is positive when the velocity is increasing, the acceleration of the particle is negative, the velocity is decreasing. So all you have to be able to do is see if the graph itself is increasing or decreasing, and that tells you if you're accelerating is positive or negative, which means am I really accelerating or am I decelerating? And in this case, I'm definitely negative because my graph is decreasing. So if your velocity is decreasing, your acceleration will be negative. And you also could describe that also with slope. You could talk about the slope of the line being negative and therefore the acceleration is negative. That would also be another way. All right, in number 4, we're looking at what is the average acceleration of the particle from 2 to 4. Show the computation that leads to your answer and indicate the unit of measure. So 2, I'm going to write it here, but it doesn't really go here. You have the velocity of 4 minus the velocity of 2 over 4 minus 2 is how you find the average acceleration. Because average acceleration is the slope calculation of the velocity, because acceleration, when you, like if I had a formula, if I took the derivative, it would make the velocity turn into acceleration. So if you don't have a derivative to take, then you can do an approximation with a slope formula. So did you get 6 minus 9 was negative 3 and 4 minus 2 is 2, so negative 3 halves or negative 1 1/2?
Yeah.
And the top is feet per second. And if you divide that by seconds, what will that turn it into? Some people call it feet per second. You'll see that in some science classes. They won't even put the 2 seconds together, which is not wrong. But it's better to say feet per second squared. All right. So what would we put with this calculation? Well, you would have reiterated the question into a sentence like the average velocity over time interval can be found by dividing the change in velocity by the change in time. Isn't that what this is? The change in velocity over the change in time? You can always put a sentence like that and then show the math calculation. And that would cover it all. It would cover what's the question about, as well as the calculation and the units and all that. All right, so with question number 5, it helps if you lay the marker down.
Wait, sorry, you said?
The average acceleration over the time interval is found by dividing the change in velocity by the change in time. In other words, dv over dt. That's what we were calculating here. But instead of using that notation, they wanted you to tell it in words because you're actually using the slope formula instead of the actual derivative formula. All right, let's look at number 5. Is there a guarantee to be a time between 2 and 4? So first of all, they're giving us a very short window here they want to look at, in which the velocity's derivative, which we know is acceleration, would be -3/2 feet per second squared. Justify your answer. So first of all, is there a possibility on here that my velocity, when I take the derivative of it and turn it into acceleration, could be negative between 2 and 4? Why? You don't think the slope could be -3/2?
But from 3 to 4 would be negative. That's right.
Right, yeah, from 3 to 4 it could be, couldn't it? Okay, so when you look at the graph, the whole interval couldn't be, but there could be one place, and this is straight, so it's not as obvious on how to talk about it, but normally these things are curves, and so you would think about right after 2, is it right after 2.1, right after 2.2, you know, all the way up to 3 and coming back down 4. Is there one place I could put that point and have that tangent line, and that slope would be -3/2? Now these are straight, so it's not quite as obvious, but that's the thought process behind it. Does that make sense so far? Okay, now that's kind of what you are looking for. Is there any reason why from 2 to 4, because of the shape of this graph, that I shouldn't even be looking for it?
Well, there's a. I don't know. This question.
You're talking about like
the one before it.
Hmm.
so basically it's saying this that you can see the an increase.
There's an increase and then there's a decrease.
Yeah. So you wouldn't even look from 2 to 3 because it's an increase, and you need it because it's a negative.
No, but that's a good thought. That's not a problem because it doesn't matter if it decreases the whole interval. As long as it does, it's somewhere in there. The problem is the point at the top. What kind of point is that? That's a cusp. And a cusp causes you to have a place that it's not differentiable. Like, you know how when you take the differentiation, you end up with a fraction, but you didn't have it before? That cusp is undefined there. It's a sharp turn. They call it a sharp turn. And when there's a sharp turn in your graph, that means it's not differentiable there. So mean value nor Rowley's theorem could apply. Yeah, and most of the time you want to talk about mean value because we're not talking about 2 places. We're just trying to find one place. The mean value cannot apply in this problem due to it not being differentiable at t = 3 for that sharp turn in the graph. So there's no such guarantee. Although it looked like it might have it, didn't it? And if you actually counted the slope from 5 up to that 3, you'd realize it's not 3/2 either. But considering that's an estimated graph, it could have been. Y'all probably didn't notice there's one problem on the top of the next page that deals with this for number 6. So if you haven't read number 6, I'd like you to try to read it and see if you can think of the answer. And I'm going to pause the video while y'all. All right. So how do you know when a particle has gone as far as it can go to the right? Well, when you start at the velocity in this problem at 0 is a positive velocity, and it stayed positive until 5. That whole section, even though it's increasing and decreasing between 0 and 5, the velocity is positive that whole time, meaning it moved to the right. But from 5 to 9, the velocity is negative the whole time. So it had to turn around at 5 and start going back to the left after that. And so that's why the time t = 5 is when it's furthest to the right. All right. Now, we're going to come back to that again tomorrow and look at some analytical algebra can get you the answers. Because if you don't have a table to look at and you don't have a graph to look at, you're bound to be able to do it analytically. All right, so now what I'd like to do is go back and look at the graphing packet that we talked about yesterday. So if you can find that.
Like you took play.
Does it?
But
All right, so first of all, yesterday we looked at taking a graph and trying to sketch out what the derivative would look like. Today we're doing the opposite. We've got the derivative and we want to sketch out what the graph would look like. Well, this is obviously a quadratic. So if you integrate a quadratic, what do you get? A cubic. There we go. So we've got to figure out what is this cubic doing and how are we going to illustrate it. Now, the one thing we don't know is to where to put our vertexes and our mins and our maxes and inflection points. We just estimate them. There's no right or wrong way to do this. What there is a right or wrong way to is having the shape, kind of, but not where the points actually are. Okay? So we know right now that this is a derivative graph. And a derivative graph, there's something special about these x-intercepts, right? So what does an x-intercept on a derivative graph tell us again? Whether there's a max or a min. All right. So this is negative and this is positive. So if you went from decreasing to increasing, what would you think that is, a max or a min? Okay. So we need to put a min somewhere on here. Now, obviously, if it's the min, we might want to put it a little lower, right?
yeah.
So we're either going to put it real low up here in the positives or even stick it down here in negatives. So let's just put it down there in negatives. Now, we got to decrease till we get to that point. Everybody agree? So something like this. Decrease till we get there. Now, what does this vertex on this derivative graph tell us? That's right. It tells us there's an inflection point. So we can put the inflection point wherever we want it. So it might be important to do the other half of the graph from the other end. So we kind of have, we can put it kind of somewhere in between. So let's move over to this other x-intercept. On this one, it's increasing and then it changes to decreasing because our derivative graph's value tells us if it's increasing or decreasing in the original problem. So if it changes from increasing to decreasing, what does that tell me that is? A max. So let's put that kind of high up on our graph because that's going to be our highest value. And it's going to decrease after that. Everybody agree?
Yeah.
So now we know somewhere between this min and that max is going to be an inflection point. And we can put it anywhere on this dotted line here we want to that's vertical. Okay? So you just decide where you want to put it. I'm going to put it right here. You put it anywhere you want to. But don't put it too high or too low or it'll look kind of weird. So now we're going to increase till we get to it and then decrease till we get to the top. Now, if we did this right, then our concavity, and that probably looks a little weird down here. I think I'll change my concavity here a little bit. It's just that point itself. I think I made this side too steep. What do you think? A little too steep? See why you want to do the rough sketch on here and get that kind of worked out? So once you figure it out, you say, well, let's think this through. It decreased and then it increased, and it's concave up on both sides, so that is what a minimum looks like. It's decreasing on both, and then it's increasing and then decreasing on each side of our max. It's concave down, so that's right. And the concavity changed from up to down on our inflection point. So I think that's a pretty good facsimile that we could draw over there and kind of clean up. What do you think? All right, I'm going to let you try the second one, then we'll go over it. So with this problem, I think we've got a lot more going on. Isn't this already a cubic?
Yeah.
So this is going to a quartic. So when you look at this x-intercept, it is positive before it, negative after it. So that's increasing to decreasing. That's a max. Everybody agree?
Yeah.
So we're going to put that point kind of high. And it decreases on the first part. And then this is going to be an inflection point that's going to be somewhere between there and the next x-intercept. That next x-intercept is decreasing and increasing, so that makes it a min. So I think I'll put that min right here, and I'm going to make it between here. I've got to get my inflection point kind of settled so I can make it the curvature right. So I think I'll just put it about, I don't know, right here. So maybe a little higher. I'll just erase it, move it. Might need to be right there. So I'm supposed to be negative all the way down to that minimum because it's all below the x-axis. So it's going to go concave. Concave. Oh, please come back. This is what you run into sometimes when you're working on something. Oh, now I got some lovely little marks on there. Y'all see those?
Yeah.
That wasn't there before. Okay, let me go back. So it's concave down on that side, concave up on this side. And so now, to get to this next inflection point and our next point that's on the x-axis, let's look at this x-axis point. It's increasing then decreasing. That sounds like another max, does it not?
Mm-hmm.
And if you kind of look, this graph is kind of somewhat symmetrical in terms of some things, but it went down less than it went up. So I don't know that that means these two maxes should be at the same place. Usually it'll be real symmetrical if they're supposed to be. So I'm going to put this one a little higher because that side of the graph's higher. And then it's supposed to be concave down after that because it's a max. And then if I put my inflection point somewhere in here, maybe about right there, I can make the concavity for each one work out to make it look like maxes and mins. Now, I don't know. They could both need to be the same because it could be this. I don't know for sure which way it is. I mean, if you think of it like this, it might be more like that because I could cut my graph in half like this, and then this inflection point would be about the same distance to the top and the bottom. So it might need to be more even. I don't know. And the thing is, it wouldn't be wrong either way because this is an estimate of what the graph looks like, not perfect. What do y'all think? Okay. So, in the packet, there's more of what we did yesterday. There's more of, here's the original graph, and then here's the derivative that you're supposed to draw. There is not more of what I just showed you, unfortunately. But this one is just a practice one. I have another one we'll do a few days from now that gives you some extra practice on both. So if you can complete the rest of what's in this one, we'll go over the answers to it and then allow you to have one for a grade. Okay? Now that's going to be your homework. The next thing I want to do today is check the homework from last night. I wasn't going to do that, but if I do that, then that will take up maybe some of our time so that Jacob doesn't get so far behind. If you're listening to this, Jacob.
I need to finish this here.
Yeah, finish that graphing worksheet. The rest of them are more straightforward. You're starting with the original and turning it into the derivative. All right. So with our homework last night, we're going to go over the answers, and if you need anything worked, you just need to let me know. Ooh, that's not going to be good for me to be putting my head down. I'm going to have to put this on the podium. Jacob, I have vertigo. Ugh, the room is going to spin. Okay, that's better. So in the first two questions, all you were supposed to do is take the derivative and see if it went back to the integral. Did it? It worked. That's fine. I mean, it's supposed to do that. You're supposed to be able to take what the integration is equal to, take the derivative of it, and go back to the integram, what was in the integration problem that they started, and it should have worked for both of them. Now, sometimes you might have to do some cleaning up
The second one, I got confused. Like,
on how to do the derivative or how to clean it up to make it look like the original problem.
looks like I got confused on both.
Okay. Well, we can look at that one.
Okay.
So on number 4, this is what they wanted you to take the derivative of, because that's what the problem was equal to, right? Okay. A little bit so you can see. All right. So first I'm going to need to divide and multiply stuff out and get it kind of all simplified, unless you plan on doing quotient rule. Okay. So 2x squared plus 6 divided by 3 square roots of x on each one. So this will be 2/3 x to the 1/2 power, because this is, no, excuse me, not 1/2 power, 1/3, 3/2 power, because 2 minus 1/2 is 3/2. And then over here, 6 divided by that's 2, and I'm going to bring it up and make it to the negative 1/2 power, so it's all powers. Now, I haven't taken a derivative yet. All I've done is clean it up. With me so far? You okay? You see what I did?
Yes. That's why I didn't distribute it. So.
Okay, that makes it harder if you don't.
Yeah.
And then, after that, you take the derivative of this. Well, if I put the power in front, doesn't that fraction go away? And 1 minus that will make it x to the 1/2 power, so that'll be the square root of x. If I put the negative 2 in front, I mean the negative 1/2 in front with the 2, that'll make the 2's cancel, make it negative 1, right? So minus. And then if I take 1 off that power, won't that make that negative 3/2? Okay. So that would be on the bottom. Is that what the original problem was? Or do I need to do more?
It says it was x squared minus 1 over x cubed.
Okay, so I need a common denominator then. So it sounds like that it was all over one denominator, which is an indication that you need a common denominator. So if I put x to the 3/2 on top and bottom, so that I can get a common denominator, 1/2 plus 3/2 is 2. So x squared minus 1 all over my denominator. So a lot of times you're going to multiply something out, you're going to just divide it out, you're going to do the derivative, then you're going to do right the opposite. You're going to put it back together with a common denominator. All right. Now, with the rewrite questions, you had to kind of clean the problem up so that you could do power rule. So in number 6, you had to bring x to the negative 2 up and say, I'm integrating x to the negative 2 dx. Then you add 1 to the power, and that makes it negative x to the negative 1 plus c. Then you bring that power down and simplify and make it negative 1 over x plus c. Number 8, first you distributed, so your integration problem changes to x cubed plus 3x in parentheses dx. Then you integrate it, and it's 1/4 x. Well, really, it's x to the 4th over 4 plus 3 times x squared over 2 plus c. And
One is to put those fractions in front.
Well, that's what the rewrite to the simplifying step does, but you could do that all at once. I don't care that you do that as separate steps. They did because that's what they were doing. You're just supposed to write it on the bottom and clean it up later. But if you can clean it up as you go, that's fine. And then it's 1/4 x to the 4th plus 3/2 x squared plus c for the final answer. Number 10, first you had to cube it. Now they took the number out, but you didn't have to do that. You could say I'm integrating 1/8 x to the negative 3 dx, but they put the 1/8 on the outside when they cleaned it up. There's no reason to do that. It's just up to you. Then if you do the power work, you're going to have 1/8, and then in next to it you're going to have x to the negative 2 over negative 2 plus c, because they didn't clean up the powers or move anything around.
So sorry, I'm slow. Did you say for number 8, you said 1/4 x to the 4th
Plus 3/2 x squared.
plus c?
So the final answer, number 10, is negative 1/16 x squared, the 16x squared is all on the bottom, plus c. In number 12, they were asking you to take a formula, and really this is more related to what we learned back in chapter 2 about going forward with derivatives and implicit differentiation. Did you think about the fact that in this problem, if this is dr over d theta equals pi, that you should move the d theta over here so that you can integrate each one? Well, that's what you do when you have that notation.
I thought that, but at the same time,
I thought I
didn't know.
I thought
Yeah.
I was just doing pi.
Okay.
So I did like pi, like 1 plus 1 divided by 2.
Oh.
Yeah, like I thought I was just doing pi.
Yeah, pi's not a letter, it's a number. So you had to know with what letter were you doing your derivative with respect to. So by taking this off and putting it over there, now you know it's about pi as a number and the letter is theta. So when you integrate dr, that means you got 1. What happens when you integrate 1? You get a letter, right? Because it's a constant, it changes to a variable. So it changes to an r. And then over here, I've got pi, a constant, so it's going to become a linear also and be pi theta plus c. Now we'll get a lot more practice with that, but that was just kind of a thrown in extra thought process here. Now in 14, was that under that same set of directions or did that start a different set?
Same thing.
Okay. This one was more obvious to me
Yeah,
because of what it was. Right?
yeah.
Isn't that more obvious? You just add 1 to the power, and put it back on the bottom?
Mm-hmm.
And that it's going to be 1 to the power is negative 3 over negative 3. So negative 1 over x to the 3rd plus c. Well, don't change it because I might be wrong.
Well, what I did was
Well, what I was going to say is if you put the dx over here and you think of it like this, then you also get what it's equal to because it's equal to y.
I fixed it to where it was the 3x to the negative 4th, but I didn't do the other step.
Oh, okay. So that's what that information in the directions meant when it said to solve the differential. It means to integrate both sides, which means you got to take away the fractional d work and put 1 on each side, just like we did when we was doing implicit. All right, number 16. The correct answer is 1/3 x to the 3rd minus x squared plus 3x plus c. Number 18, it's 2/3 x to the 3/2 plus the square root of x plus c.
Was it not? I got a 2 in front of me.
I'm gonna need you to work it.
No, it won't have a 2 in front of it because of something that happens. I can show you that. Do you need me to work what?
18.
Okay. All right, we can come back. Well, I'm going to work that. Let me call out a few more answers. That way we can see if there's more than one. Number 20, it is 4/7 x to the 7/4 plus x plus c. Number 22 is negative 1 over 3 x cubed plus c. Number 24 is x minus 1 over x plus c. Number 26, 4/5 x to the 5th minus 4/3 x to the 3rd plus, excuse me, not x, it's supposed to be t's. I said x's, plus t plus c. And then number 28, 1/3 t cubed plus 3/4 t to the 4th. Why are they not in order? I put them in order. 3/4 t to the 4th plus 1/3 t to the 3rd plus c. I know the problem's not in order, but you should put your answer in order. All right, so besides number 18, is there something else you'd like so I can write more than one up at a time?
I just thought of problem 18.
Just 18? Well, you know what I think that is? I think it's fractions more than anything, but I could be wrong. I don't think it's the calculus. I think it's the algebra. Or maybe just numerical number stuff. We'll see. Because it's a little trickier. So in this problem, I'm going to change that to x to the 1/2 and 1/2 x to the negative 1/2 to integrate it. Does that make sense so far? Did you do that part right?
I don't have to.
All right. Second thing. If I add 1 to the power, won't that be 3/2? And won't that flip it in front and make it 2/3? So you don't have to put the 3/2 underneath it. You can go ahead and flip it because you know it's going to flip. And then if I add this to 1, I get a 1/2, which makes a radical. And if I divide by a 1/2, how do you divide by a 1/2? You flip, multiply. They cancel. And that's why it's just the square root of x plus c on the end. Does that make sense? Because these cancel.
So for those two, that x could just cancel out too?
What x?
Right there, the 3/2, or is that just?
No, that's part of the answer.
Oh,
3/2 x to the, 2/3 x to 3/2 plus the square root of x plus c is the answer. Now number 30 was a lot easier.
Yeah.
3t plus c. Number 32, 1/3 t to the 3rd plus cosine of t plus c. Number 34, 1/3 theta to the 3rd plus tangent of theta plus c. 36, secant of y minus tangent of y plus c. Number 38, secant of x plus c. What would you like to see worked from those?
38.
yeah.
Just 38? 38 takes quite a bit of trig substitution,
Yeah, that's what I was trying to look for.
or at least I'm thinking there's quite a bit. So first of all, the problem with this one is you've got a subtraction problem on the bottom. And that subtraction problem wouldn't be an issue if it didn't have squares in it, because we don't have squares on top. So the first thing you should always do when you see a square is go look at Pythagorean identities, because Pythagorean identities deal with squares. They're the only ones that deal with squares. And there's only one of them that deals with sine and cosine. Sine squared plus cosine squared equals 1. So you take out the 1 and you put in sine squared plus cosine squared for it, and I already have sine squared in the problem. I'm not going to write words out. It's too much trouble. Does everybody see what I'm talking about? Sine squared plus cosine squared makes the formula 1. So I took out the 1 and put in the sine squared plus cosine squared for the 1. Took this out, and I put this in. What happens to my sines? They cancel. So now I've got sine of x over cosine squared of x dx. And we know yesterday, when we had one that was squared and one that wasn't squared, we did what?
We separated them.
We separate them. So that's going to be 1 over cosine of x times sine of x over cosine of x dx. So now that's going to be secant tangent. And secant tangent's derivative integrates, whoop, not dx, plus c. Secant tangent's the one that has the 2 words that the first word is the answer for the integration. And it doesn't need a negative on it because it doesn't start with a c. Alright. So is that it? You feel pretty good about the rest of it?
Yeah.
Okay. Alright. Well, since we only have 20 minutes of class left, I don't want to start word problems today. So I'm going to let you just work on your worksheet for homework. So to finish up your graphing worksheet, and that way I can convert this video for Jacob.